In today's lesson, we are going to be looking at vectors. So this is just going to be a quick introduction to vectors. If you've taken a physics course, then you may have already looked at vectors. So this might be familiar to you. If not, this would be something new. You wouldn't have covered it in a previous grade 11, 9, or grade 9, 10, or 11 math class. So vectors are basically, we will talk about the components and what they're kind of, or what makes up a vector, but they do include directions, and there's ways we can describe the directions, right? So one, if we have a visual, right, a boat is shown moving in the direction, right? So we can see that it's headed in this direction, right? We can see north and we can see the angle. Now, if we wanted to represent that in what we call true bearing, true bearing is basically a 3-digit number that represents the number of degrees clockwise from north. So in this example, it would be 320 degrees, because if we go clockwise from north, that's 320 degrees. So we'd be saying its heading, the true bearing is 320 degrees. If we wanted to do what was called quadrant bearing, then we basically measure between 0 and 90, and we measure east to west of the north-south line. So we're basically using north, south, east, and west to kind of give our directions. Right? So we might say that it's north 40 degrees. So I'm north and I go 40 degrees west, right? Because west would be over here. You could also say west 50 degrees north, starting out west and going up north 50 degrees. So there's different ways that you can describe it, but these are going to be the kind of two main ways that we look at. So I'm just going to fill out a chart based off of those measurements, right? So true bearing again is the full measurement from north, so going clockwise. So in this case, this would have to be 120 degrees. The quadrant bearing would be south 60 degrees east, or we might say east 30 degrees south, because there might be two different ways to describe it. Quadrant bearing, south 10 degrees west. I'm going to draw this one first, because it's going to be a little bit easier to draw than to figure out the true bearing. So we have south 10 degrees west. So we're at south. North is over here. South, and we go 10 degrees west. So that would be my vector. That would be my direction. If I wanted the true bearing, that is going from north. It's going from north clockwise all the way to that point. So that would be 270 plus 10, or sorry, 180 plus 10. So this would be 190. 90 degrees for the true bearing. Again, I'm going to draw it first because it does tend to be a little bit easier to visualize and to help figure out the other bearings. So 90 degrees. So if I go north and I go 90 degrees, that takes me right to here. So for the quadrant bearing, I could just say east. Right, that's my direction. I'm just heading east. You might also say north 90 degrees east. So you're at north and you turn 90 degrees and you head toward or turn 90 degrees in the eastern direction. Again, this is just a elaborate way to say east. Right? You could do south 90 degrees east, same idea. It's just an elaborate way where you can just say east. So with vectors, the movement of a speeding car, predicting the weather, improving the performance of athletic equipment, right? All these different things, they involve vectors. So what is a vector, right? If you've seen the movie Despicable Me, you've seen the bad guy, his name is Vector, and he has a saying that he commits crime with two things, and that would be direction and magnitude. And that is actually what vectors are made of. So direction and magnitude. And then geometrically, a vector is represented by a line segment with an arrowhead, like we see here. So we would say this is the vector AB. We draw a line with an arrow on top, or it might just be a symbol with half an arrowhead. But that would be the vector AB. Now, if we have a quantity that does not have a direction, that is considered what we call a scalar. And that's where there's a magnitude only. So that might be something where we look at just speed, right? So a speed of 50 kilometers per hour, right? It might just be a mass of 3 grams, right? If there's no measurement or no direction, it's considered a scalar. Now, two vectors are equal if they have the same magnitude and direction. So they have to have the same magnitude and direction. The position is not important. So for example, if I had a grid and I had a vector like this, we'll call this x, then an equal vector would be something like this. Even though they're not on top of each other, they have the same direction and magnitude. Now we can show the magnitude of the length of a vector using what we call absolute values. And that is just where we have two parallel lines on either side of our vector. And that's basically just telling us, so these lines, those are the absolute value signs. And basically just means that we're always dealing with positive values. So regardless of what direction our vector is going in, our magnitude will always be positive. And vectors with the same magnitude pointing in opposite directions are what we call opposite vectors. Again, for example, if I have a vector here, we'll call this vector A. Vector B would be going the same magnitude, but going in opposite directions. So something like that. So in our first example, we want to draw a scale diagram to represent each vector quantity. So we are going to try to be as accurate as possible because we're making a scale diagram. Right, so I want to draw the vector that's 60 kilometers per hour due west. So we have a magnitude, we have a direction. I need to draw it heading in the west direction. So I'm going to come up with a scale first. So I'm going to say that 1 centimeter is equal to 20 kilometers per hour. Right, because that way at least I know how long or what my magnitude is going to be. So in order now to show that, I would need to draw a line or a vector that is 3 centimeters long, because 3 times 20 would be 60. So we can go 1, 2, 3. I'm going to use actually a different color just so it stands out a bit more. So my ruler doesn't really have any markers or units on it, so I'm just going to assume that we see here from, can't really show it on here, but if I just show the ticks like from here to here, though, that would be 1 centimeter. That's what I'm just going to go by for this lesson. But if you have your actual ruler, you could do that. So this is my vector. Call it, I don't know, it's 3 centimeters. We can call it, say, U. For B, vector AB, which is 2.5 centimeters north, 45 degrees east. So here I have a different direction. So I need to use a protractor. I'm going to use this ruler because it does show the angles. We're going to get 45 degrees. I'm going to draw my vector. Here I'm just given a length, so 2.5. So we have 1, 2.5. Again, I am approximating a little bit. And then we have the north 45 degrees east. So that would be our vector, AB. So we'll say A and B. So that's our vector AB. Example 2, now we want to state the magnitude and direction of the quantities represented by the vectors below. So I'm told that this vector is drawn with a scale of 1 centimeter equal to 50 newtons. So I have to figure out what is the length of this vector. Again, it's going to be approximate based on what I'm using as a ruler. So if I line it up, we can see that we have 1, 2, 3, 4. So we're getting about 4 centimeters. So 4 centimeters times 50 newtons equals 200 newtons. The other component now, depending on how we're going to write this, I need to have the degrees. I can use the true bearing, so I can go from 180, or I can go from north, or I can use my coordinate or quadrant bearing. So I can use going from east or south. Right. So again, I'm going to use my protractor a bit. So I'm going to basically see what this angle is. It looks at it like it's about 19, 20 degrees. I'm going to say 20 because that's a nice round number. So if it's 20 degrees from this line, that means that this entire thing would have to be 110. So for my vector, I could say u, so the absolute value is equal to 200 newtons. I could say 110, or I could say 200 newtons, and then I could say south 70 degrees east. Because if I know that it's east 20 degrees south, then the opposite from here would have to be 70 degrees. So different ways you can name it. You could say east 20 degrees south if you wanted to as well. Or just stick to the true bearing. For B, again, same idea. Let's get a measurement first. Again, we're going to approximate it based off of our ruler and what we're using for our markings. So we see it's about 1, 2, 3.5. So 3.5 centimeters. And I know that 1 centimeter is equal to 120. So I'm going to do 3.5 times 120. I get 420. So right now I know that my vector is going to equal 420. And then I need a measurement. So I could go from north, right, and work all the way around. I do need to figure out what either this measurement is here or this one here. Either one would work. Let's see what we get with our ruler. Oops. So I'm going to start off here at 90, and if I go back, it doesn't want to go. Looks like about 50 from 90, so that means that this angle here is 40 degrees. So I could say, if that's 40, sorry, then that means that from clockwise from north, that is not 360, that is 320. So I could say that vector W is 420 kilometers, and I could say at 320 degrees. Or I could say 420 kilometers north, 40 degrees west. Or I could say 420 kilometers west, 50 degrees north. Right, so a lot of different ways that we could represent that in terms of the direction component. Lastly, for C, again, I'm just going to roughly measure what my vector is or how long my vector is. We say we got 1, 2, 3, 4, 4 and a bit. I'm going to say 4 just to make it nice and easy. 4 centimeters, right? If you're looking on your page, it might be a little bit different because I've zoomed in here, so obviously it looks a little bit larger. So 4 centimeters. Because it's dealing in millimeters though, right? This is the same thing as saying 40 millimeters. So 40 times 7.5 equals 300 kilometers per hour. So my vector then, vector V, is going to be 300 kilometers per hour. And the direction, now we got to go back and use our protractor. Looks like it's like 13 degrees. 13 to 15. I'm going to say 15 just to make it easier. right? Just easier values. So 15 degrees. If I'm coming from north, though, that would be 90 plus 15, so 105. So I could say that my vector v is 300 kilometers per hour, 105 degrees, with a bearing of 105 degrees, or I could say 300 kilometers per hour with a bearing of east 15 or 15 degrees east or south of east, or east 15 degrees south. Right, I could work the other way and go backwards from south and say, well, if it's 15, then this has to be 75. So I could say 300 kilometers per hour south, 15 degrees east, or 75 degrees east of south. Again, different ways that you can word that direction. For 3, what is west 20 degrees south or 20 degrees south of west as a true bearing, and represent this as a vector? So I'm going to draw it first to make it a little bit easier. Right, so west, and then I go 20 degrees south. So there's my vector. Don't really have a magnitude yet, but that's okay. That's 20 degrees. My true bearing is the one that's coming from north. So 180, oops, that looks like 28, but it's not. It's 20 degrees. So 180 plus, this would have to be, or not 60, it would have to be, shoot. This little component here would have to be 70 degrees. So then that means from north, it would be 190 plus 70, or sorry, 180 plus 70, or 250 degrees. So then this means that, we'll call it vector x. Say this was 2 centimeters, 2 centimeters, 250 degrees, right, is the bearing. What is 284 degrees as a quadrant bearing, and represent it as a vector? So again, I'm just going to roughly draw a vector diagram, or a grid, or coordinates, or directional, or compass, whatever you would like to call it. So north, 284. So that means that I am going full round. So 190, 180, 270. Then I hit my mark. 284 degrees. West would have been 270, so this is 14 degrees. Because I can use that now in my for my vector. I'm gonna use x again, absolute value. Let's say it's 2 centimeters. Again, just magnitude we don't know, but just have something there. So 2 degrees, and for the quadrant bearing, we're going to say west. West 14 degrees north. You might also say, instead of that, or 2 centimeters north, 76 degrees west. Just basically, if this is 14, then this other component has to work out to 90, which would be 76 degrees. State the following as a vector, both bearing and quadrant bearing form. So again, I need to measure it. Again, I'm going to roughly measure it based off of my markings. So we'd say 1, 2, 3, say 4. So this is 4 centimeters. I need my angles. First, I'm going to get the angle from basically east. So I have to go down. What's the angle here? Looks like about 20 to 22. I'm going to say 20 again, just it easier. So 20 degrees. So if that's the case, then from north it would be 110. From south it would be 70. I have enough information down to write out my two forms. So vector A is equal to 4 centimeters. Quadrant bearing, or sorry, true bearing would be 110 degrees. Or I could say 4 centimeters, say south, 70 degrees east, or 70 degrees east of south. I could use the 20 as well. So this lesson is just basically looking at the introduction to vectors, right? Understanding that vectors have a magnitude, whether it's a length, a speed, a force, whatever the case may be, as well as a direction, right? So a vector has to have two components, just understanding the different ways that we can write them and the different ways we can represent their directions as well.